Hello, so on the bench today we have an Agilent E4418B RF power meter. Agilent, I wish they hadn't changed that name from HP. Now of course it's changed its name again to Keysight. I think Mr. Hewlett and Mr. Packard would be turning in their graves, having their very high quality test equipment company changed name over the years, but that's progress, I guess. So this device measures RF power, which, as you may or may not know, is a very hard thing to do accurately. Even, well, I mean, you can buy RF power SWR meters, but you're looking at 10% or maybe, if you're lucky, 5% accuracy on those things, and they're usually fairly limited in their frequency response. Even the Bird series, the famous Bird power meters made in America, I think they only quote an accuracy of 5%. So I've never really had an accurate way of measuring RF power. I mean, I can use the spectrum analyzer, but there again, that's not designed to measure accurately. It's always got an uncertainty of maybe plus or minus a dB, something like that. So the only way to accurately measure RF power is with one of these beasts, and I picked this up very cheaply. I didn't get a power sensor with it, because that's the other point about these things. They need a separate power sensor, and they come in varieties of different types which cover different frequency ranges and different power ranges. So these are fairly easy to get, but very, very seldom do you get them with a power sensor or a cable to connect the power sensor. So I had to buy the power sensor separately, as I said. And the power sensor I got is here. It's an 8482A power sensor, 50 ohm input, 0.3 microwatts to 100 milliwatts. So it's basically got a range of 53 dB, and that's more or less what you'd expect. That's the dynamic range of the sensor, although more modern sensors, I believe, that Keysight produces now will go from minus 70 dBm to plus 20 dBm, whereas this one basically goes from minus 30 to plus 20 dBm. So that's an incredibly big range though, isn't it? That's 90 dB if you're talking minus 70 to plus 20. But this one is good enough for what I need, and certainly this was very cheap. If you want something more, what should I say, exotic, you're going to be paying up to 1,000 or more. But this was nowhere near that. This was just over 100 for the power sensor. And normally when you get these power sensors, they have a list of calibration tables on the back of the sensor. But this one's got a hideous little graph, because the response of the sensor will vary across its frequency range, and the frequency range on this one is 30 kilohertz. No, is it 30 kilohertz? Yeah. No, it's not. It's 100 kilohertz up to 4.2 gigahertz. And if I get something to point with, as you can see, it varies considerably over the range. As you get really high in frequency, you're dropping to 90% of the accuracy at its main frequency, lower frequency, whatever. But and the standard reference point for calibrating these sensors, or calibrating your power meter, is at 50 megahertz, and at that frequency this has got a 99.4% correction, which you have to load into the meter you're using. As I said, they normally come with a printed table. If I can get this one. This is the one I got out the handbook, the manual for the meter, and this is for the 8482A. This is an average they've taken over many sensors, and this is what you would expect if you haven't got the calibration data for your sensor. Then you could use this. But looking at this table, the results I've measured off that graph as best I can are a fair bit different. In other words, at 50 megahertz they're saying 98%, I've off my graph it's 99.4, and so on and so on, all the way up to 3 gigahertz, whereas they've got 93 at 3 gigahertz, 93%. Mine is 96% as far as I can tell on that rather poor graph, and I haven't bothered with 4.2 because I'm never going to use it that high. In fact, I'll never use it at 3 gigahertz. So back to the instrument. What you do is, when you want to use the various sensors, you go into I think it's measurement setup. Right, measurement, no it's not, it's system inputs. And then you've got a thing called tables. I'll perhaps zoom in a bit on that. Tables, and then you can go to sensor cal tables, and then it's got a list of all the popular sensors, power sensors that would plug into this. And there you are, it's the 8482A. That's not the one I will use, because that's, as I said, is just the average. But you can put in your own. So I've gone down to custom, which is number 11 on there, and if I select that, or edit it if you like, that's where I've set in all my values, starting at 100 kilohertz and going all the way down, right to 3 gigahertz, basically at 96%. So I've done with that, and that's the one I've got turned on. So all the measurements it takes will be in with reference to that table. So get out of that. And now what we've got here is the main screen for when you're doing measurements. And what I do like about this, it's got a digital display on top, it's a dual screen, and at the moment it's just reading the noise floor of the sensor, but you've also got an analog screen down there, which is like a bar graph, I guess you could say, and you can set the parameters of that analog screen. When I got this machine, it had its lowest reading at minus 70 dBm, which is pointless, as my sensor only goes down to minus 30. So I've reconfigured that to minus 40 anyway, and plus 20 at the top end. Of course, you've got to be really careful with these things, these power sensors. These are the most expensive bit, really, or they can be, and if you destroy the thing, you've had it. And this one's got an absolute maximum of 300 milliwatts power into it, but I wouldn't go above 100 milliwatts just to be on the safe side. So if I was going to measure high power, which I'll demonstrate later on, I'd use an attenuator in front of it. So yeah, I really don't like that graph. It's almost like it's been put on afterwards, maybe, I don't know. So what you have to do now, once you've got your sensor connected, you first of all press 0 cal, and ideally you'd have this unit on for at least half an hour before you do any of the calibration, because you want it to warm up and stabilize. So first of all, you don't input a signal into the sensor, disconnect the sensor, and then you press 0. So now it's zeroing out the sensor. Takes a few seconds, not long. And it's coming out of the noise floor of the sensor. And then you want to connect your sensor, and I'm going to use a right angle connector because it just makes it easier, right angle N type. And here we've got on the front panel a power reference signal which is generated inside the unit and traceable back to national standards or whatever, and this produces a 1 milliwatt signal, very accurate 1 milliwatt signal at 50 megahertz. So now I press cal and it'll go ahead, turn the power reference on, 1 milliwatt, and it'll calibrate that, and then turns the signal off again. But if I now turn power reference on again, it comes out at exactly 0 dBm. So that's 1 milliwatt it's reading, and it all hinges really on the calibration of this reference. That's what all your measurements are going to be referenced to, this 1 milliwatt output. So if that's screwed, you're screwed in your measurements. So what should we do now? By the way, this particular sensor uses a thermocouple, or 2 thermocouples, and that's how they measure the power in heat, basically. And when you think about it, this thing's working down to a microwatt, although it does say 0.3 microwatt. Let's call it a microwatt. Imagine measuring a microwatt of heat, and that's what these things do. They measure down to those sort of levels, 1 microwatt of heat. Okay, here's a rather crude drawing of how this thermocouple power sensor works. You've got your end plug on the end of the sensor, and then it comes into a DC blocking capacitor, and after that it goes to 2 100 ohm resistors, which are capacitively coupled together on each end. So effectively at RF they're going to be a 50 ohm load, and on each resistor, imagining these are very tiny little resistors, you've got a thermocouple on each resistor, and the thermocouple will then sense the heat change as you apply RF power to the thing. Then the thermocouple connections go out on gold wires, 2 gold wires, and off to the rest of the little circuit in the power sensor. And there isn't much in there. There's only a couple of FETs and a transistor, and I guess they're just amplifying the very tiny amount of voltage they get from the thermocouples. But when you think about it, to be able to measure a microwatt of heat, these resistors must be pretty tiny, because you've got to sense a temperature change of a minute temperature change on those 100 ohm resistors. And of course they do other types, which are other types of power sensors. They used to use what do they call them, thermistor sensors, and the other ones they do now are diode, well, they have in the past as well, diode sensors instead of thermocouples. And diode ones seem to have a bigger dynamic range, something like -70 to +20 dBm. Anyway, that's a quick description from what I got out of the Agilent paper I downloaded. Right, what I'm going to do now is I've set up my RF generator at 50 megahertz and 0 dBm output. Unscrew this. First of all I'll turn the power reference off, not that it really matters, and I'll unscrew this, and I'll take this cable and I'll screw it into my RF generator. So, as you can see, and my generator's been on there for an hour or so to stabilise, it's measuring 0.15 dBm, so that's not bad, is it, for an RF generator, which I don't know when it was calibrated. I've had it over 2 years, and that's at 50 megahertz, so I think that's pretty good. Now, if I drop the output of the generator, just an example, by 10 dB, so I have to go to minus 10 dB, it's more or less the same as far as offset from, you know, 10 dB, minus 10 dBm. So that's good, that's working fine. Let's go to minus 20. Still measuring more or less exactly what you'd expect. Now let's go to minus 30, which is close to the lower level of the sensor. So maybe a bit of inaccuracy. Also, I've noticed it takes time to settle as you get lower in power level, because I guess because you're measuring such a very small amount of heat. Yep. So I think that's pretty close anyway, even though it's close to the bottom end of the sensor now. So if I go below that and I go to let's try minus 32 dBm. It's struggling a bit now. It's trying to, yeah, it's really struggling to cope with that. So yeah, that's the noise floor of the sensor, really, I think you're seeing there. Well, if I go back to 0 again, another thing I can do with this thing, I can switch it between dBm and watts. So my generator at 50 megahertz is producing 965 microwatts, so that's quite nice. And I'll switch it back to dBm again. Okay, let's try a different frequency on the generator. Let's go right up the top of the shot, shall we? Let's do 2 gigahertz. See what he thinks of that. Right, that's 2 gigahertz, 0 dBm. Now, you can't just measure that without adjusting the power meter, because it thinks you're still measuring 50 megahertz. If you can see up there, it says 50 megahertz. So it's taking that calibration table and it's allowing a correction at 50 megahertz. So I have to go in here, this is a bit I find a bit annoying. Every time you change frequency, you've got to change this. So now I've got to change by doing all this. I think it would have been very nice if you'd put Packard or Agilent or whatever they call themselves had put a keyboard on it, because it's a matter of moving across the display and stepping up and down. So now I've set it to 2 gigahertz, and now I know that's correctly offset with the table to measure accurately. So my generator is basically producing 0.3 dBm at 2 gigahertz. I'll just see what it's like at gigahertz. Okay, now I've got to go through all this procedure again. Set it to 1 gigahertz, and it's minus 0.1 dBm. I think that's a reasonable output for an RF generator, because even they're not guaranteed more than about plus or minus 0.5 dBm accuracy across that whole range. I think I'll do one more test down the lower end of the scale, right down at say 100 kilohertz. Right, I'm now inputting 100 kilohertz, but of course I've got to change all this again. Frequency, and no, I can't do it that way because it hasn't got a kilohertz button. So I've got to go all through this to get to 100 kilohertz, which is the most annoying thing about this thing. So it's 0.1 megahertz I want. So, right, now it's adjusted itself for 100 kilohertz, and as you see I'm reading almost exactly 0 dBm. Let's have a look and see how low I can go before I get some inaccuracy. So if I go below 100 kilohertz, which is what this sensor is rated at, no, it's 30 kilohertz, isn't it? Okay, let's take it down to 30. And it's starting to drop off a bit. So I'll sort of change that really, shouldn't I, to 30 kilohertz. Okay, so I'm just going to assume that my generator drops off at 30 kilohertz. But it's the right, now looking at the calibration table, it's 100 kilohertz is the minimum. So yeah, you would expect it to be a bit down at 30. And if it'll go any lower than that. That's 20 kilohertz, so yeah, it's fairly inaccurate now. And that's 10 kilohertz, so it's 5 dB down. The sensor is 5 dB down at that frequency. So that's an interesting little test. Let me think of something else to do. Okay, I'm back at 50 megahertz, and I forgot to check above 0 dBm. See what it's like as I go up in power level. So I'll go to 10 dBm, and as you can see my generator is reading 9.86 dBm. Okay, now let's go up to the top of the shop, 20 dBm. And my generator will go up to 25 dBm, which is 300 milliwatts, but I'm not going to go any higher than that. So as you can see, 19.85 dBm. So I think that's fairly good for the generator and for the power meter. Right, I think what I'll do is now I'll check one of my homemade attenuators. Okay, right, I'm back at a 1 gigahertz signal from the generator and 0 dBm, as near as damn it anyway. And what I'm going to do is, this is one of my homemade attenuators. This is a 20 dB homemade attenuator. I did a video on how I made this. and when I made it I tried to make it as perfect as possible, and it was fairly flat right up to nearly 2 gigahertz. That was testing it on a spectrum analyzer, but now I'm going to stick it on this and see what we achieve. I'm going to put this in series with the RF output and I should get -20. But first, before I do that, I'll do a relative thing. If I press rel, that zeroes it out, right? Well, it should zero out. It does. So now I'm going to disconnect the output and stick the attenuator in. Okay, so that's a homemade 20 dB attenuator. As you can see, it's reading 19.93. And that, for a homemade attenuator at 1 gigahertz, I think that's pretty impressive myself. Dare I say it, having made it myself. So that's all good. I think finally, if I put it back out of rail mode, yeah, that's what it's reading. That's the true reading in dBm again. So I think, okay, well, I think this video has gone on far long enough, so I hope you got something out of it. And here is the meter in its final resting place, and I had to move a few things around, but the idea is just generally stack it higher and higher. And so thanks for watching. I might do a little follow-up video on a couple of Baofeng handheld radios to see if they do really produce the power output that they are advertised as. Now I've got something I can accurately measure RF power with. So thanks for watching, bye for now.